Okay, in this practical, I'm changing the mass hanging on the end of the string. I'm recording the extension. I've already got the original length and the cross-section area written down. I want to find the Young's modulus. So what do I need to plot to get the Young's modulus? So firstly, Young's modulus is stress over strain. I'm just going to rearrange this and make extension of the subject here. The force comes from the weight that's hanging on the end of the string, so that's mg. Okay, so if I put that in, I've got this equation. Now I'm going to compare it to y equals mx plus c. Now considering that I have the extension and I have the mass, and those are two things I'm changing. So what I could do is I could plot extension on the y-axis, and on the x-axis I could plot the mass. So the thing that's multiplying it, so that should give me a straight line going through the origin. There should be no y-intercept. The thing that's multiplying the x-axis is the gradient. So in this case, GL over area and Young's modulus, because that's going to be my gradient. So once I do changing y over changing x and I find the gradient there, I have to find the Young's modulus. The Young's modulus is going to equal the gravitational field strength times the original length divided by the cross-section area times the gradient. Okay, in this circuit that's shown here, I'm going to change the resistance of the variable resistor, and I'm going to record the current and the terminal voltage. Okay, I'm going to try to find the EMF and the internal resistance. So I need to write the equation that links these two. So EMF is equal to terminal voltage plus a loss PD, and loss PD is just current times resistance. Rearranging this slightly, I can get terminal voltage, which is the thing I'm changing, and current is also something I'm changing here as well. We'll find the EMF and the internal resistance. So comparing that to y equals mx plus c is just easier if I write like this. The reason is because I'm going to plot the terminal voltage on the y-axis, and on the x-axis I can plot the current. And so I'm going to get a straight line with a negative gradient. Negative gradient because the thing that's multiplying the x is minus r. Okay, so that's going to be our gradient, and we're going to have a y-intercept of which is the EMF. So once you've figured out the change in y over change in x across the line like this, you'll have to do minus of the gradient to get the internal resistance. And then the EMF is just the y-intercept. Okay, in this practical, I'm measuring the time taken for a car to move between two light gates. I'm changing the distance between the two light gates, and I'm trying to determine the acceleration a here. Okay, and also the initial speed the car was passing to the first light gate. So the equation that links them is s equals ut plus half at squared. Now normally u is 0, but in this case it isn't, which makes it a lot hard to deal with, because it's being multiplied by t here as well. So the best thing to do here is actually divide both sides by t, as you get s over t equals u plus half at, and then compare it to y equals mx plus c. Okay, so what I'm going to do is actually on the y-axis I'm going to put s over t. So that means I'll have to come up with a new column for s over t, which has units meters per second. Again, the x-axis I'm going to plot time. So this means I'll get a straight line with a positive intercept. Okay, so the gradient is going to be equal to half a, and the y-intercept is going to equal the initial velocity like this. So once I've gotten the gradient here, which is half a, so a will equal 2 times the gradient. And if I want the y-intercept, that will just give me the initial velocity straight away. Okay, in this practical, I'm changing the length of the pendulum, and I'm recording the time period of oscillation, probably over multiple oscillations and then averaging it. Okay, I want to analyze the data and find the acceleration due to gravity. The equation that links these together is this one here. So I could plot t against square root of L. But what I'm going to do is I prefer to square both sides. I get t squared and then the 4 pi squared here, L over g. So comparing to y equals mx plus c, I could just plot t squared on the y-axis. So I'll have to come up with a column for t squared. And on the x-axis, I'm going to plot L. So the thing that's multiplied, so this should give me a straight line going through origin. There's no y-intercept here. The thing that's multiplied the x is 4 pi squared over g. So that's going to equal my gradient. And so if once I figured out the gradient by changing y over changing x, I can get g by doing 4 pi squared over the gradient. Okay, in this practical I have a search coil that's inside a coil of wires just producing a magnetic field around it. There's an EMF induced inside the search coil. I'm changing the angle of the search coil from normal, and I'm measuring the EMF induced. Okay, so the equation is given to us here. V0 is the maximum voltage, and we're trying to find the maximum voltage. I want to show that the relationship is in fact V equals V0 cosine theta. Now if I plot a V against theta, then I'd get a curve. What I want to do is I want to get a straight line. and I wouldn't know what curve it was, so that's why I need to turn it into a straight line. So I'm compared to y equals mx plus c. On the y-axis, I can plot the voltage, V, EMF induced, and on the x-axis, I'm actually going to plot the whole cosine theta there. So that means I'll have to come up with a new column here for cosine of the angle in degrees, and if I plot this, I should get a straight line with no intercept, like this, and my gradient will equal V naught. So that gives me a gradient straight away, and the fact that it's a line tells us that this relationship is correct. Okay, now final practical here we have a discharging capacitor. We're measuring the current at different points in time, and we want to analyze the data to find I naught, the initial current, and the time constant RC. So the exponential decrease in the current here. And the best thing to do here is take natural log on both sides. Okay, the right hand term here can be separated using our log rules. Okay, and then e to the power natural log of e to the power minus t of rc just becomes minus t of rc, like this. Then compare it to y equals mx plus c. On the y-axis, we can plot natural log of the current. So we'll have to come up with a column for that, where ln I with it in amps there. Okay, and on the x-axis, we plot time, and so we should get a straight line with a negative gradient. The gradient is equal to minus 1 over rc. And we should have a positive y-intercept, which is equal to natural log of the current there, I naught, initial current. Okay, so once you got the gradient by doing change in y with change in x, to get RC, the time constant, which is what we're looking for, you'll do minus 1 over the gradient, like this. And because the y-intercept is equal to ln I naught, to get I naught, you'll have to do e to the power of the y-intercept.